Hi, in this video I'm going to show how to use the MATLAB Deep Learning Toolbox to detect digits in images. So we're going to use a convolutional neural network to do this experiment, and we're going to use this dataset provided by MATLAB in this folder, the digit dataset. This is similar to what we see in MNIST in Keras. It has 10,000 images, 1,000 images per digit in each folder, and the folder is gonna serve as the label for the digit. Okay, so in order to do this, we're gonna use data stores, which is a central concept in Deep Learning Toolbox. MATLAB provides various sets of various data stores. Image data store is one of them. Some of these data stores are able to manage a huge amount of data, a very large amount of data. So you can see more information there. So first, let's create the data store. For that, we have to specify the folder path, which is this one. Okay, let's get the path. And now let's create a data store. Since the images are in subfolders, we have to set this option include subfolders to true, and also infer the labels for supervised training of the neural network. The labels are going to be inferred from the folder names. And with that, we get our image data store after, of course, providing the label to those files. Okay, now we're going to specify in that data store the batch size. Batch size is basically for training a neural network, is the amount of samples which the neural network is going to run in training before recomputing, updating the weights of the neural network. Okay, now we're going to do some pre-processing of the data before the actual training. And this is gonna be done when training the neural network. But for now, we specify it as a transform object. So this transform is gonna transform the data store. Sorry. But still, we get a data store in here as an object. The actual callback for pre-processing is gonna be run again while training. So this function could be an anonymous MATLAB function, or you can define your own function. In this case, I define a function in the same folder. And so what the function is going to do is going to take the list of images, and they are each of the images are going to be rotated by a small angle using this image processing toolbox function. And then that same image is going to be placed in the left column, and in the right column we're going to use the labels that is coming from the info, that by setting this argument to true, we are indicating, I suppose, that this information is going to be passed. Okay, so now we have the data store ready for training. Now let's create the layers for the neural network. So we basically create an array, a MATLAB array of layers. The first layer is the input layer, and it's going to be an image input layer to receive the image, like the Keras MNIST dataset. The images are very small. They are 28 by 28. And the first layer is going to be convolution. In MATLAB, the first argument is going to be the size of the window for the kernel convolution operation. You can specify a tuple in here, a pair of values. If you specify a pair of values, you can optionally have different non-equal dimensions for the kernel. But if you only specify one value, it's going to be a 5x5 window kernel for the convolution layer. This is the number of output features. So we're going to have 20 output features, and for regularization, we're going to use a ReLU layer. This pair of convolution layer and ReLU layer are very common for the front-end layers of the convolutional neural network. And then we follow it by a max pooling layer of stride 2, and kernel window size is going to be again 2 by 2. So convolution layer is gonna find local features, like for example connecting edges, doing morphological transformation like open, close, delete, erode, and but for detecting an image, that is a global object that you want to detect. So you want to detect patterns between different places, and that's why the max pooling is for. Basically, it's like the convolution detects something in one place, and then another piece detects something else, and the max pooling it detects things between these two convolution patterns and so on. Basically, it basically assembles the pattern, so eventually we detect global patterns through the max pooling. Finally, after we do the preprocessing, we do a fully connected layer, and this is for actually classification, detecting the final pattern, and the outputs are going to be 10 because we have 10 digits. We want to detect digits. And softmax layer, and this is going to enable us to have something like from 10 options, give me the one with the highest probability, and we also reinforce that with classification layer. Okay, now that we have the architecture for detecting the digit, we're gonna supply the training options. The training options specify the type of training that you're gonna use, the training algorithm. There are at least 3 listed options. ADAM is one of them, which means adaptive moment estimation. In the Keras video that recorded previously, we were using root mean square propagation, and also you can use the famous stochastic gradient descent. Okay, in addition to that, you can specify that you want to plot basically display the progress of the training, and also the number of the size of the batch. Again, is the number of samples that the neural network is going to process before updating the weights, and the weights are updated through the algorithm that you specify in here. So there are other options that you can specify, the learning rate, validation data. You can specify validation data, which is very important. Not doing that in this example, and so on. Okay, so now let's do the actual training of the network. For that, let's put a breakpoint here, because this function is gonna be executed when training the neural network. Okay, so we're gonna do that with this. Okay, so now you can see that we get a list of images, and the number of rows is 128, and we only have one column for the images. So we have 128 rows, so we're going to create a cell array with the same number of rows for all the images and 2 columns. The first column in the left is going to be for the image, and we're going to rotate it as mentioned before. And the column in the right is going to be the label that is derived from the folder. Let's going to run an example. So in here, let's display this image. So if we have a 0, that is kind of rotated, but that's and now after rotation it's gonna look like this. Well, let's rotate again, because it doesn't look very rotated. Maybe the random rotation didn't do much. So let's watch it again. Okay, it's not rotating much really. It's kind of the same. Let's keep trying. Well, I have seen it rotating. For some reason it's not rotating, but anyway, that you get the idea. This is an image processing toolbox function, and you specify random angle to rotate. And the label in this case is gonna be 0. Oops, not completed the parentheses. It's gonna be 0. So let's keep going in this, and you can see that you're assembling a list with the rotated image on the left and the labels in the right. This is a random pre-processing for the data for training, but similar technique can be used to augment the data That is, for example, if you have a small set of images to train a neural network and you want more training data, what you can do is that the small set of images that you have, you do some affine transformations on them, like translation, shear, warp, rotate, and things like that. And with that, you can multiply the amount of data that you have to train your neural network. Okay, so let's keep going. Let's finish this preprocessing, and the neural network is gonna start training. So in as mentioned before, the video I made for this same example, training a convolutional neural network for detecting digits in images using the MNIST dataset in Keras, achieved a 99% accuracy, but again, it was done with more data. They had 60,000 images, and in addition, the layers that were using that example were more than one convolutional neural network and a convolutional layer and max pooling pairs. So it had more layers. So you expect, because of the amount of data and the the more layers, you expect a better accuracy. This is a very nice thing that MATLAB has. You can get to see the loss lowering as time goes by and the accuracy increase. And I in the previous time I tried, it reached to 98%, which is pretty good for having less layers and less data. And it doesn't take that long. Okay, so you can see here at the beginning you have a huge loss because the weights are far off predicting the value. So the weights are going to be modified to decrease the loss using the Adam algorithm mentioned before, and the accuracy is going to increase from 14%, which is worse than random, and it's going to make it all the way to 98. I'm gonna pause this until this finish training because it takes a while. Okay, it finished training. I'm surprised this time it reached in one of the epochs to 99%. I'm gonna bring back the command that was used for training. You provide the data store in there, you provide the layers architecture that we created, and the options that include the algorithm that you're gonna run. This is a little bit different from Keras, in which you have like a big object for models, and the model, you add the layers in that object and use that same object to train it and to compile it. But in here, the layers are separate. Then you have the training as a function, and finally you have the net object after you train it. And the data is separate, etc. So it's like a separate commands and separate objects. Okay, so this is the data structure for training, the layers and the options. Okay, now we train it. We achieved a 95% of accuracy, but maybe with more epochs or less epochs, we could have something like this. Okay, so now let's gonna test this neural network on an image. Let's go to the folder, and we have all the trees in here. So we're gonna load one of the files in there. We're gonna load it, and we're gonna show. So we loaded number 3. So we're gonna test if the neural network is able to detect this tree. So let's predict it with the test image. We're gonna pass the test image to the network, the trained neural network, and we're gonna call the predict method. And this should give us tell us which digit we have. So the output is gonna be as shown in the layer. You have 10 features in the output. Let me get into a command. So the final layer was the classification layer, but there was a fully connected layer. This one is the one that does the classification, and you have 10 features, and those 10 features represented these 10 digits. So this is the probability, and by adding these 2 layers at the end, you have a more beautiful number in here. And you can see that the probability for 0, 1, 2, this corresponds to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 0, 1, 2, 3. The probability for number 3 is 100%. For the other ones is 0. So it precisely predicted that this is a digit 3. So we were able to test that it works with 95% accuracy. And thank you for watching the video.